Hello. So last time we have introduced something that is called a quotient group. And what exactly are we doing with quotient groups? One of the primary reasons for studying quotient groups is that we are studying, of course, a new kind of group. That is, given a group, we are constructing another group. That is very helpful, especially in finding examples and all. Okay, so that is exactly what we are doing with quotient groups. We are constructing a new group from a given group. That is, if you are given a group G, let G be a group, let G be a group. Okay, if you have to construct the quotient group, you first of all need a normal subgroup of G. Let N be a normal subgroup of G. What did we do when constructing the quotient groups? We say that this one, it is the quotient group. So what do we collect in quotient groups? The elements of the quotient groups are cosets. So that is why I'm denoting it with a big letter X, because a coset is, after all, a set. X, it has to be a coset of n in G, x equal nx, where x is an element of G. So remember, in quotient groups, every element, it is a coset. Let us have an example. And the operation I forgot to mention, it is the multiplication of cosets. But again, we are just using the word multiplication, but of course it can be addition or something else. For example, okay, maybe I don't need this one right now. What do you mean by multiplication of cosets? We mean this: if x is a coset and y is a coset, that is x, because it is a coset, will be in this way, x equal nx. And similarly, we will have y equal ny, because it is a coset. By multiplication of the two cosets, we mean this, nx and y. But because n is a normal subgroup, so nx and y, it will become nxy, which is again a coset. So this is what we mean by multiplication of cosets when n is a normal subgroup. Nx and y equal nxy. So let us look at an example. So let's see. Let us have G to be the set of integers with respect to plus. If because G is abelian, every normal subgroup of G is normal. So let us take a subgroup of G. That subgroup will automatically be normal because G is abelian. So let us have N. We have seen that this one, it is a subgroup of G minus 3, 0, all multiples of 3. If you refer the previous content, you will see this, that this one, if you include all multiples of 3, this one will be a subgroup. In fact, this one, it can be written, because it is multiples of 3, you can write it as 3z. It contains all multiples of 3. So this one, it is a normal subgroup because G is abelian. N is normal since G is abelian. Since G is abelian. Abelian over here in the sense that A plus B will be equal B plus A for all A, B belongs to G. So let us see, because G is normal, because N is normal, we can form the quotient group G by N. So what can we have in this case? It will be the set of all x such that x, it is a coset, and x for all, where x belongs to G. And over here we have to be very careful. It has to be the operation of the group. So over here will be x such that x equal n plus x actually. Okay, because the operation of the group, it is plus, where x belongs to G. So x, it is a coset. If you remember, how many cosets does n have? N, it has three cosets. If you remember, it has three cosets. The cosets are n plus 0. The distinct cosets are these, n plus 3. So again, what have we done? We have constructed the group G by n, the quotient group, and we have found that these are the elements of the group: n plus 0, n plus 1, and n plus 3. N plus 0, you can easily write this one as n. Okay, n plus 1 and n plus 3. So these are the elements of the quotient group G by n. As an example, it is interesting to see that because the quotient group contains only the distinct cosets of n, so what can we say? How many elements does G by n have? How many elements does G by n have? How many elements does G by n have? Because we are collecting cosets, so as many as there are distinct cosets. As many as the number of distinct, right or left, you can use any word over here, right or left, because n is a normal subgroup. Every right is a left coset, so it doesn't matter whether you use the word right or left. So that's why over here I've written right or left coset. That is order of G by n. Order, it means the number of elements of G by n. It will be equal to the index of n in G. How many elements does G by n have? As many as the number of distinct cosets. That is the index. Actually, we will prove another theorem regarding this one, where we will get that it's actually equal to order of G divided by order of n. Okay, but that is another time. For now, we will jump to another topic, that is homomorphisms. So what is a homomorphism? This is actually one of the very important concepts in group theory. So we have studied groups, we have learned to construct another group, that is the quotient group, but we also need to study the relation between two groups or between three groups or whatever, and for that we need homomorphisms. And if you have to study the relation between two sets, one of the things that you have to use are functions. So that is exactly what we are doing with homomorphism. It is just a function. It is just a function, but of course we are using a different word for it, homomorphism, because that function will satisfy some conditions. An extra condition, okay, that is why we are calling it with another name, that is a homomorphism. And because we are dealing with groups, and groups are just sets, so homomorphism is a function between two groups. Let G, over here I will use G with the operation star, and another G, I will use this symbol as an O. B and G dash O be two groups, just to show that they are different. So what is a homomorphism? A homomorphism is a function f. It is a function f from G to G dash. Again, over here we are using the word, the letter f. Actually, we can use another word for another letter for this one. You can use it with G, you can use it with H, you can use it with theta, phi, anything, okay? But because it's only natural, okay, a function will denote it with f. Okay, it is a function from f from G to G dash, satisfying f AB equal FA FB. So over here, because we have a space in between, what should we fill? A and B, they are the elements of G. For all A, B belongs to G. A and B, they are the elements of G. So that is why over here, if they are the elements of G, we will use star. Whereas over here, FA it is an element of G dash. Similarly, FB, it is an element of G dash. Here A and B are elements of G. FA and FB, they are elements of G dash. So in between FA and FB, it will be the operation of G dash, that is this O. Okay, so this O is in between FA and FB. Alright, so a homomorphism is just a function between two groups which satisfies this one. FA star FB equal FA or FB for all A and B belongs to G. Before we look into examples, I think it is best if we can have two theorems regarding homomorphisms. Let us see. We will do examples, but I feel it is best if we can have two theorems first. Let's see. Theorem. Theorem number 1. If F, actually I also forgot to mention about this. Some books, they no longer write FA star B equal FA or FB. They will simply write it as FAB equal FA FB. But it should be understood that in between A and B is the operation of the first group. In between FA and FB, it is the operation of second group. But they don't write it down anymore. It should be understood. Operation of first group. And over here it is the operation of second group. So even if they don't write down, you should know that it is there. So let us have that theorem. The first theorem says that if F from G to G dash, again with the operation star and O, is a homomorphism, then this is a theorem FE equal E dash. That is, the identity of the group G is always sent to the identity of the group E dash. E, it is the identity of G, and E dash, it is the identity of G dash. So always, if you have a homomorphism, then the identity of G is always sent to the identity of G dash. If the identity of G is not sent to the identity of G dash, you can immediately conclude that it is not a homomorphism. So let us prove this theorem. The proof of this theorem is actually very simple, but you have to remember this first line. If you forget this first line, then you are done. Okay, you can no longer proceed. This is actually okay, FE star E. Okay, maybe I'll erase this. I'll use this just to show that there is difference between this star and this star. This star means it's very important. FE star E equal FE. This is true. This is true because E star E is equal to E. So you will have it. But because it is a homomorphism, FA star B will be equal to, so instead of A, you are having E. Instead of B, you are also having E. FA star B equal FA FB. Sorry, instead of B, you are also having A. You will have this. Alright, so this is what we are having. Next, what will we do? So this one is actually an equation. It is an equation in G dash. How do I know that it is an equation in G dash? Because this element, it is an element of G dash. This element is also an element of G dash. This element is also an element of G dash. So all the elements are elements of G dash. That is why I say that it is an equation in G dash. So what will I do next? we can multiply by the inverse of Fe. The inverse of Fe. Okay, both sides multiply, but over here because we are in G dash, it will be O multiplied by the inverse of Fe. Okay, you will have this, and on the right side you have Fe, again O Fe inverse. So what will we be having? Because it is a group, G dash, it is a group, so you can combine this one and this one first. What will you be having? An element times its inverse in G dash, so you will have the identity. An element times an inverse in any group will be equal to the identity. So that is why over here the identity of G dash, it is E dash. So that is why we are having A dash. Similarly over here we are having an element times its inverse. So we will be having the identity E dash. So now we are done. Therefore, an element times E dash, an element times the identity will give you that element. Remember something like this: A star E. It will be equal to A, right? So it doesn't matter even if you replace by maybe Fe. Instead of A you are having Fe, and instead of star you are having this operation O. Instead of E you are having E dash, you will still be having Fe. This works for any group in fact. Okay, an element times the identity will give you the element. An element composed with the identity leaves the element unchanged. So by Fe O E dash, it will give you Fe. And the right hand side it is E dash. So this completes the proof. So this is theorem 1. This one is actually very important. As you will see when we are doing examples, it will become more easier. Let's see. Okay, the second theorem it says if f from G to G dash is a homomorphism, then Fa inverse is equal to the inverse of Fa. Fa inverse equal to the inverse of Fa for all A belongs to G. Again, this one is a very straightforward proof, as you will see again, but you will have to remember this first line. This first line is very important. This first line, for this one it's this, because you need A inverse, right? You need A inverse. One of the equations involving A inverse is actually this, right? A star A inverse, it's equal to E. A is an element of G, that is why I'm using star. Star is the operation of the first group. A star A inverse equal E. So you can also have this. You take F on both sides, you will have this. This line is very important. But because it is a homomorphism, you can actually split this one. So always remember, in homomorphisms you can split, you can recombine, you can do anything. Fa, but if you split, the operation of the new group, of the group G dash, will be present. And over here will be Fe. So now what will we do? We will multiply both sides by the inverse of Fa. So multiply both sides on the right by the inverse of Fa. So you will have this. Again, it is in the group, Fa inverse. Fa inverse will be equal to, multiply both sides by the inverse. You will have this Fe. So you will have this. So let's see the next line. The next line is actually very simple. The inverse times an element. It's just like this one. If you take FA as x, x inverse x, how much will you get? You will get the identity, right? But over here the identity will be E dash, because this is an equation in E dash. This is an element of G dash. This is an element of G dash. So it will become identity dash E dash. So this is what I'm saying. The first one will give you E dash times FA inverse. And from the first theorem, how much is FE? From the first theorem, how much is FE? The first theorem says that FE will be equal to FE will be equal to E dash. E dash. So we are done. Identity times an element will leave you with the element. And similarly over here, an element times the identity will leave you with the element. So this is very important. Again, this completes the proof. So the inverse of FA, it will be F of A inverse. Again, very important. So with these two theorems, let us now look at some examples of homomorphisms. Why am I doing those two theorems first? Because actually, when we are given an example, we first have to have an idea that it is a homomorphism. That is, we have to quickly see whether there is a possibility or not that the given function is a homomorphism. Okay, for example, number one, f. Again, if we have to give an example in group theory, we first have to specify the groups. Okay, let us take ZZ plus and G dash. Again, the same group Z plus. We can do this. Okay, so both the operations are the same in both the groups. So let's see. And a function from Z to Z, from G to G dash. Suppose we define by fx equal 1 for all x belongs to Z. So this is just an example. If I ask you, is this one a homomorphism? What will you say? Is the answer yes or no? The answer is actually no. Okay, as you will see why. So let us just first have a visual representation of this one. Fz to Z, all elements goes to 1. So this one is the set Z. These are the integers, minus 1, minus 2, 1, 2, and so on. Similarly, over here we are having the set of integers, all integers 1, 2, 3, and so on. What we are doing with this function, fx equal 1 for all x, that is, all elements goes to 1. Okay, so is this one a homomorphism? The answer is no. The answer is no, because we don't even have to use the definition. Now we will use the theorem. Just take a look. What is the identity of this group? The first group it is Z plus. The identity it is 0. E is equal to 0. For the second group, what is the identity? For the second group, the identity it is again 0, because it is Z plus. So how much is Fe? How much is Fe? Fe will be F0, right? F0 according to this picture it is 1, because all elements are sent to the number 1. So even 0 is sent to the number 1 by F. 0 is sent to the number 1 by F. So it is unequal to E dash. Because it is unequal to E dash, because Fe is unequal to E dash, we can immediately say that F it is not a homomorphism. So that is why I did the theorem first. Okay, so this one is an example of a function that is not a homomorphism, a function between two groups. Let us see a function that is a homomorphism. Example number 2. We will have g equal z plus, okay, and maybe g again will be z plus. I am still doing with integers. And now we define f from g to g dash. We can actually denote it by g, it doesn't matter, f from z to z. Sorry, f from z to z. Define it by fx equal 2x. Okay, fx equal 2x. Let us have a visual representation. Is there a possibility that it is a homomorphism? Let us see. Okay, 0, minus 1, minus 2, and so on. 0, 1, 2, 3, 4, and so on. Similarly, over here we'll have minus 4, minus 3, minus 2, minus 1, 0, 2, 3, 4, and so on. Okay, they are both the same sets. 0, where is it sent to? It is sent to 2 times 0. That is, it is sent to 0. 1, it is sent to 2. 2, it is sent to 4. Minus 1 is sent to minus 2. Minus 2 is sent to minus 4. So this is a function. It is a function, and similarly 3 is sent to 6. Minus 3 is sent to minus 6, and so on. E, for the first group, it is 0. E dash, it is 0. So is Fe equal to E dash? Yes, Fe is equal to E dash. Because F0, it is 2 times 0. It is 0. It is equal to E dash. So there is a possibility that it is a homomorphism. So because there is a possibility, let us try to prove it. Okay. For the first example, we immediately have that it is not a homomorphism. That is why we did no proofs, no nothing. But for this second one, there is a possibility. So let us prove. We will prove that the second one, it is a homomorphism. If we have to prove, let us take a look at the definition. Okay, let us take a look at the definition so that you will understand why we are starting in that way. Let me just find that page. Okay, so a homomorphism between two groups, it's this. You have this word for all AB belongs to G. So this one is your starting point. If you have to prove that F is a homomorphism, you will have to start with this. For all AB belongs to G, so you will start with that A and B belongs to G. What do you have to do? You have to show that FA star B equal FA or FB. So let me go back to that page. Okay, so what will we do? We will start with let A and B belongs to G over here at Z, so Z. To prove, we need to prove F A star B. Instead of star, what will we be having? Star, it is the operation of the first group. Over here it is plus. And we need to show that it's equal to FA. What is the operation of the second group? The operation of the second group, it is again plus FB. We need to show that FA plus B equal FA plus FB. For all A and B belongs to Z. So if you have to prove this one, just start from the left hand side, get it equal to the right hand side. Left hand side, actually I used to do it like this. FA plus B, how much is it equal to? Fx is equal to 2x, right? Fx is equal to 2x. So even if x is equal to A plus B, what will you have? If x is equal to A plus B, you will be having 2 times A plus B, right? You will be having 2A plus B. So this one you can immediately write down as 2A plus 2B. And let us just have a look at the right hand side. How much is it equal to? Right hand side. For proving homomorphisms, okay, even though you can immediately write down this one as FA plus FB, okay, this works for this one, but why am I starting from the right hand side? Because sometimes it is very difficult to go from the left hand side to get it equal to the right hand side straightforward. That is why we have to start from two sides separately. So right hand side, it is fa plus fb, 2a plus 2b. Okay, for this example it's very easy, but as you will see, okay, there will be some examples where it's actually more difficult. Okay, therefore left hand side equal right hand side, so that is why it is a homomorphism. Therefore fx equal to x is a homomorphism. All right, so with this example, I think it is enough for today. I will send some more examples in the WhatsApp group, but for now it's all right.